Everyone, buddy, welcome back. So let's do some problems with oblique shocks. Okay, let's try it out. Now in this case, I'm going to have an oblique shock, and it's going to be a wave angle of 30 degrees. And it's in a Mach 5 flow. What do we know? Well, we know the upstream pressure is going to be equal to 26.5 kilopascals, and the upstream temperature is going to be equal to 223.3 Kelvin. Can we solve it? I hope so. We're going to find out. And we want to find the pressure, temperature, Mach number, total pressure, and total temperature after the shock wave. And we also want to find what the change in entropy is across the wave. My goodness, we want to find everything for this problem. And we're going to do it all. We're going to do it all. Okay, so how are we going to do this? Well, the first thing is we're going to probably need to go ahead and find what our shock wave is going to be, or what our Mach number is going to be after the shock wave. Now, remember, when I come up to a shock wave, only the normal component of the velocity actually experiences shock. The tangential component does not. So if I have a Mach number of 5 here, make sure I do this right. There. I'm going to have two components. I'm going to have like Mach tangential 1 and Mach normal 1. And only the normal component actually matters. So now this is a 30-degree angle. This will also be a 30-degree angle right here, and this is my Mach number. Boom. So if I want to find my normal Mach number to begin with, that's going to be equal to my Mach number to start times sine of 30. So it's going to be equal to 5 sine of 30, which is equal to 2.5. Okay. So if I want to figure out what's happening across this table, when it comes to the shock, I now have to go to my normal shock properties table. Okay, so I'm going to do that. So I'm going to go find the normal shock table, and that is actually in the back of your textbook in Appendix B. So let's go ahead and jump there right now. Now I'm in your textbook right this second, and we're going to go to Appendix B. So I open the sidebar, I go to Normal Shock Properties, and I'm just going to jump right there. And here it is. Now for a Mach number of 2.5, I'm going to have to scroll down. Wait. Gotta be careful here. I hate how they do these things. Yes, there we go. So for a Mach of 2.5, which would be right here, we can find all the properties we need. So I go ahead and make it so I can actually draw my screen so you can make sure you're seeing the same thing as I am. Okay, so 2.5 happens right here. I hate that they do this to you, but they do it times 10 to the power of 1. So even though this is 0.25, it's actually 2.5. And they do the same thing in all of these places. Maybe it's just my textbook, but I hate when they do this. So the first column we come into is going to be equal to our pressure ratio. So this is going to be P2 over P1. This right here is T2 over T1. Oops, that's not, my bad. One more over. This one right here is T2 over T1. This one's equal to P02 over P01. And let's see, that's all we're going to need, I believe, from these tables. So we're going to grab these three values. And we should have everything else we need from that. Okay, just want to show you where this came from so you're not confused when I have these values suddenly. Tables are super important for oblique shocks, for normal shocks, for expansion fans. Go use the tables. So let's jump back to the problem. Okay, and here we are. So now I want to use the values I found to help me solve for the rest. So I had that P2 over P1 is equal to 7.125. T2 over T1 is equal to 2.137. And P02 over P01 is equal to 0.499. Oh, one thing I forgot to mention is also we can find our normal Mach number afterwards, which is going to be equal to 0.513. That was another thing I should have grabbed. Okay, so we have all that information, and it makes it pretty easy to find a few of our properties. First off, it's really easy to find our pressure afterwards, because P2 is just going to be equal to P2 over P1 times P1. So that's going to be equal to 7.125 times 26.5 kilopascals, which will equal, let me see, I believe 189 kilopascals. It jumps up there. Woo! Okay, not too bad. We use the tables, we make it easier on ourselves. Now let's do the second temperature. So T2 is going to be equal to T2 over T1 times T1, which will be equal to, let's see, 2.137. That's just from the tables, times our initial temperature, which was 223.3. Yes, 223.3 Kelvin. Equals 477.2 Kelvin. There we go. Beautiful. Okay, so we got a little bit here. Now let's go ahead and find out what M2 is going to be. Okay, now M2 is going to be equal to my Mach number 2 over sine of beta minus theta. Okay, now where in the world does theta come from? That comes from, sadly not a table, it comes from a diagram. It's not nearly as easy to see here. There's also some relations you can use for it, but it's from a diagram right now. So let's go to that diagram and find it out. Here we are in the sidebar once again. As a note, for most of the problems, I think this is given to you usually, so you don't have to jump back to the tables. But I want to go ahead and show it to you in your textbook so you know where it comes from. So you have to go to Chapter 9, Oblique Shocks and Expansion Fans. And I believe it's in the oblique shock relation section that you'll find what we're looking for. So I'm going to scroll down and I'm looking for a for a diagram. I wish it was a table, but it's not. It's a diagram. And here it is. Okay, so the bottom gives me my angle theta. The side gives me my shock wave angle beta. And then I have all these ideas here. So what I'm looking for is, let's see here. I have my normal Mach number of, sorry, not normal Mach number, my regular Mach number of 5, which is this line right here. This is going to be impossible. I'm just going to go ahead and write my screen. What am I doing here? Making it too hard on all of you. Okay, so first off, I'm going to go across with 30. Because that's my wave angle, I already know that. Now let's trace down my Mach number of 0.5, which is this line right here. Intersects right there, I go straight down, and I hit, boom, 20 degrees. Okay, so that's kind of how you can do it. I know there's a whole lot there, and there's way too many lines. It gives you headaches, I'm sorry. But that is how I would find my angle theta for this equation. So I did it. Okay, so with that, let's jump back to our problem. Okay, so we found it from the diagram, and so now we can plug everything in to find out what our Mach number is behind the shock wave. So it comes out to be 0.513, because that's what we got from our tables earlier, over sine of 30 minus 20. And what's that come out to be? That's equal to 2.95. Okay, that's good. We've got a third of the things we're looking for. Whew. Can we find everything else? I really hope so. We're going to find out. Oop, went too far there. Sorry. Now we have a few more things we're going to need to find out. So the next thing we're going to work on is finding our total pressure, P02, and our total temperature, T02. Because we're going to need those both. Now, if you're wondering, like, what about total pressure? We weren't given that. You're right. We 100% weren't given that. However, we can, you guessed it, find our total pressure, P01, from the tables. So let's go back and figure out what P01 is. So if you're wondering where this is, it's in Appendix A here. So Appendix A gives this to us. And this is the isentropic tables, because we're assuming that before this point, it was an isentropic flow until it got to the shock wave. And so we're going to look at it for a Mach number that's equal to 5. We're going to figure out what P01 over P1 is, as well as what T01 over T1 is. Because it gave us our pressure and our temperature. If we know those, we can find P01. So let's jump back there and find it. Okay, here we are. And let's get to Appendix A. So I scroll down here and I find Appendix A. There we go. Mach number of 0.5, or Mach number of 5. So I need to go up higher, way higher. Going a ways. Okay. Am I ever going to make it there? There we are. Finally got to it. So let's go ahead and write on the screen now. So right here, I have my Mach number of 0.5, and then I want to find the rest of the information that I need. Let's see. This column right here is my T01 over T1 column. And this column right here, yes, that is the P01 over P1 column. Okay, so we can get our total pressure and total temperature using those two values. So one, 529.1, the other one is 6. That's for a Mach number of 5. I always want to say 0.5 because it's the way they write it, but it's 5. It's 5. Okay, now let's jump back to the problem. So we now know what these two values are. So I can say this one's equal to 529.1, and this one is equal to 6. And so if I want to find my total pressure after the shock, well, I can just kind of use the chain rule. So I already know what P02 over P01 is. And now I know what P01 over P1 is. If I multiply that by P1, well, guess what? P1 cancels, P01 cancels. What am I left with? P02, right? Works out pretty well. So we can plug in all of our values that we've gotten from earlier. So we got 0.499 for P02 over P01 times 529.1 times the initial pressure of 26.5 kilopascals. And that comes out to be a massive, my goodness, 700 kilopascals. If I did my things right. Yeah, that should have been right. 700 kilopascals. So, quite a bit. I feel like I might have had a number off on there. Let's see. Nope, that works out fine. Ah, no, I did it wrong. Sorry. 7,000 kilopascals. I believe that is correct. 500 times 20 is 1,000. Nope, it's 700. It's 700. I'm just being crazy. There you go. Okay. Did it right the first time. Now we're going to do a very similar process to find our total temperature afterwards. Luckily for us, the total temperature doesn't actually change. So T02 is going to be equal to T01. That's not changed by your shock wave. And so that's going to be equal to T01 over T1 times my initial temperature. So I plug in the numbers I have. I have 6 and I have 223.3 Kelvin. That comes out to be 1,339.8 Kelvin. Glorious. Okay, the last thing it asked us to calculate, we have calculated so much for this problem, but the last thing it helped us to calculate was what is the change in enthalpy? Or better yet, let's write it out as what is S2 minus S1, so we can just calculate at both points, and we'll go there. Now, whether or not you know this is going to be related to my change in total pressure. It's equal to negative my specific gas constant times the natural log of my change or my total pressure. So it's not a really hard equation at all, honestly. It's going to be equal to negative 287 natural log of 0.499. That's just taken from the tables, which comes out to be equal to 199.51 joules per kilogram Kelvin of entropy change. It goes up. It has to. Okay, that was everything. So we saw the tables, all kinds of tables. We saw the diagram. We saw how we used those to calculate all the things we needed for this problem. Thank you all for listening. I hope this helps you, and I'll see you all next time. Bye-bye.